Okay, so my aim today, I was told that I could do a very, that the point of the summer school was to actually have some broad topics, and I told them that I don't do quantum simulation at all, very aggressively so. And they said, no, we promise. We just really want you to teach people about quantum sensing and what the state of the art is in quantum sensing. Okay, so my aim is, in the first hour, what I'm going to do is just give you a primer on the physical platform, and when people say quantum sensors, what exactly are they talking about when they're not talking about LIGO? And then the second hour, I will tell you some research that uses these things for various tasks, and like a few new ideas that I have some baby ideas about how it can connect to quantum simulation eventually. Okay, so let's try it. So normally I would read these notes and then decide, pick and choose what I'm actually going to write on the board, but this time you guys can see that process in real time, some kind of honesty. So the physical platform that we're talking about is the Nitrogen Vacancy Center in Diamond. This is probably 90%, I would say, of the quantum sensing work going on in the world that does not have to do with just interferometry and photons or atomic, fountains. So it's been a very successful sensor. And first, let me explain why, and then a few principles of, how hard it would be to find another one of these. So you sort of have to understand the physical basis, and then what people mean when they say that they're using it as a sensor. Okay, so what the NV Center is an atomic defect in diamond. This is really key because this, in principle, gives you nanoscale resolution because you have something that really does act as a point sensor. So as long as you can now place that thing next to something else with roughly that same distance scale, then you can imagine actually having, being able to take advantage of this atomic resolution. And the reason that the NV Center is very special is really just for three reasons. One is that even though it's in the solid state, you have extremely long spin coherence. Normally, if you put anything in the solid state, you have interactions with the lattice, and then that destroys basically your qubit degrees of freedom, and you usually have like sub-nanosecond coherence times for just about anything at room temperature. But for NV centers, you get these spin coherence times of on the order of milliseconds, and the T1 limit is really 10 milliseconds. So it's a remarkable object that is best in class by more than an order of magnitude. Just as importantly, you have to actually be able to talk to that spin. So if we just relied on spin resonance techniques, which are very insensitive, then you would usually need, say, 1 billion of these things to be able to see any signal. So being able to do kind of single atom manipulation requires, in general, that you have some kind of optical interface to these spin degrees of freedom. So there is a convenient method just using off-resonant light for optically initializing and then also reading out the spin. Okay, and what do I mean by this? I think there's probably at least a handful of actual cold atoms people in the room. And in cold atoms, this optical initialization and readout is totally trivial, right? You just find like 2 resolvable states that give you nice cycling transitions and selection rules, and then you can use that to just say, how many photons did I get when I tried to shine resonant light with this transition that's off-resonant with this transition? So the reason that this is really challenging in the solid state and at room temperature is that all these transitions are just broadened out. So there's no way to do kind of the normal stuff you would do with cold atoms, where you just have a resonant laser, and then you ask how many photons I get back. So here we're going to have to rely on something like kind of weird. And then because of that, that we inherit a bunch of technical problems downstream from that one thing. But it also makes this center somewhat rare, that there are not that many solid state objects where you have this kind of convenient off-resonant optical initialization and readout tool. Okay, so the very broad idea is that what we're going to do is just use this optical spin readout combined with some kind of spectroscopy to measure the NV spin Hamiltonian. And then that reports on something like the Zeeman splitting, which then gives us the B field local to the NV center. And then that is our sensor. Okay, so the most natural thing that we can do is measure magnetic field. There's other things that you can do too. They're all kind of sucky, to be honest. So we'll just talk about magnetic field sensing. And then, somewhat better than just doing the static spectroscopy, which many of you will already be familiar with in the kind of language of quantum control, is that what you really want to do is create a superposition of your eigenstates and do a Ramsey measurement, right? So you're going to put the NV center on the equator of the Bloch sphere, let it accumulate phase from some magnetic field, and then do some projective measurement that maps the phase onto a population. Okay, so yeah, I think this is like one of those things that I would normally skip, but so in general, I would say that most of the work in this field has kind of focused on just using this thing as a static magnetic field sensor, right? So I can now just take my NV center. You guys can see my cursor, right? Yeah. I can just take my NV center, stick it in like an AFM tip, a little diamond cantilever, and then scan that over a surface. And then now I just have an object that can compete with all of the other magnetic sensors that exist in the world, like spin polarized STM, scanning squid magnetometers, magnetic force microscopy, magnetic resonance force microscopy. So, everything else that kind of looks like this. It is actually a competitive technology along those lines because you can have sensitivities that are like nanotesla per root hertz. So they sort of compete with things like squids. But you can have much, much higher spatial resolution in principle because this thing is now an atomic sensor. But I would make the argument that these experiments are really nice, but there's actually an entire other kind of universe that is a little bit less explored, which is that because this NV center is a qubit, we now have a rich set of tools to be able to use this NV center to measure fields where the mean value is 0. Okay, so noise. So if you go around, I don't have to just look at the world and ask, can I measure a static magnetic field? But I can also ask, what are the fluctuations of the magnetic field across many different frequency ranges? And the part that makes this really interesting from a condensed matter physics standpoint is that this now gives us access to dynamics, which are otherwise incredibly difficult to measure when you think about kind of normal probes, and also even correlation functions, which is what I'll spend a lot of time talking about. All right. So our general scheme here is that what we're going to do is combine 80, 90 years of nuclear magnetic resonance where we know all these pulse sequences and can drive our qubit with different Hamiltonians to make it sensitive to different components of the noise and all kinds of things. And then we combine that with something like 40 years of single molecule microscopy, which people have known how to do since the 80s, in order to pinpoint a particular location where we're going to measure these dynamics. I guess the benefit of not having to draw this on the board is that I don't have to draw this monstrosity on the board. All right, so here's what the NV center structure is. You have a diamond lattice, which is just the same as the silicon lattice, but much smaller. So it's an FCC lattice with a basis. All of these things are carbon, and they're all sp3 bonded, so you just have all these tetrahedra. And then the kind of nice thing is that with diamond, because this is such a tight lattice and you have such strong bonding, you have an enormous band gap. It's 5.5 eV. So that gives us a very large optical transparency window for putting things in. The nitrogen vacancy center is something that forms when I just take 2 of these carbons out and then put in 1 nitrogen, and then I have a vacancy in the lattice. And then so this guy sits in there, and I guess I didn't. Right, so normally I would actually draw where these are in the band gap, but it just turns out that this gives you extremely deep electronic defect levels, and then this 5.5 eV gives you enough headroom that I even have orbital excited states of this NV center that are also deep electronic levels. So for the atomic physicists in the room, to 0th order and 1st order and even 2nd order, I can really think of these as linear combinations of atomic orbitals and molecular orbitals, and I don't have to think about the surrounding diamond lattice at all. Which is very nice. All right, so our actual qubit states are built out of, we can do some electron counting. My nitrogen gives me 2 electrons from the lone pair. I have these 3 dangling bonds that are pointing in that each give me 1 electron. And then if I put all those together, that forms the neutral nitrogen vacancy center. The one that everybody actually works with is the negatively charged NV center, which has 6 electrons. And then now what I'm going to do is just fill up those 6 electrons in, some set of orbitals. So what we're going to write down are the symmetry allowed linear combinations of various orbitals. What you would actually want to do is like DFT to figure out what these are, but from group theory, we can already make some pretty good guesses. So like a reasonable basis is the nitrogen lone pair in these 3 dangling bonds. And then I can say this thing has C3V symmetry, so I'm going to write down all of my kind of allowed combinations, and that gives me A1, A1 prime, EXEY. And then from DFT and also from a couple decades of spectroscopy, we know that this is the correct ordering of the single particle wave functions. And then we fill them up, and we get this as our ground state. So I have a ground state S equals 1 spin triplet. And this gives rise to all of the normal S equals 1 spin basis states. And this is what I'm now going to use as my qubit states. Any questions? It goes by a lot faster if I don't have to write it on the board myself. OK. For anything that is greater than S equals a half, you can also have electron-electron interactions that then give rise to more splittings. Okay? So in particular, if you have dipolar interactions, you can imagine that if these electrons are kind of side by side, then if I try to put them next to each other, then these guys are going to see a repulsive interaction, whereas these guys will see an attractive interaction. So now, even without applying a magnetic field, I would expect my ms equals 0 to be lower in energy than my ms equals plus and minus 1. And then, just depending on how exactly these electrons are actually organized in space, you will get different magnitudes of this ordering. So this is called a zero field splitting, which means that at 0 magnetic field, I already have a natural splitting between the states. And for NV centers, this is at around 3 gigahertz, which is the equivalent of applying 1,000 Gauss effective field. So the dipolar interaction is actually very large. There's a similar kind of zero field splitting that happens in the orbital excited state, but it's about half the value. OK, so in general, what all of our experiments are going to look like is that I have some microwave source around 3 gigahertz. I'm going to use that to manipulate the spin ground state. And then I'm going to use photons. I'm going to use light to either initialize the spin or count photons on the way back and read it out. OK, so that's my ground state. And then from my single particle states, it's relatively easy to now start to build up orbital excited states, right? So I can do things like move one of these electrons from A1 prime to EXEY, or I can build up spin singlet combinations. And then now I can start to draw an entire kind of orbital energy diagram that shows where all of these different configurations are relative to the band gap. So here I have a spin triplet manifold with my ground state and my first orbital excited state. Don't sweat the term symbols too much, but the energy splitting between these is 1.9 eV. So this is a red photon. There's also a singlet manifold that is slightly shifted in energy that has a 1.2 EV splitting, which means that you could, in principle, use infrared light to access that. And there's a number of people who are working on trying to do, for example, better spin state readout by using kind of both colors of photons. OK, so the key thing, which I already sort of alluded to, is that if you look at these positions relative to the valence and conduction bands, these are extremely deep electronic defects, right? So at room temperature, this guy is 3 eV away from the conduction band. That's not going to ionize. It will just stay there forever, right? As long as you don't shine light on it and screw things up. So you have these extremely deep defects, which means that you can have closed optical cycles without just auto-ionizing this state, right? So I can now really do all of the things that we imagine doing in atomic physics. If I go to low temperatures, I can actually do orbital selective optical transitions and then do all the kind of normal set of tricks that you have for cold atoms. All right. Any questions before I go into optical dynamics? Yeah.
Are those numbers coming from calculation or explicit math?
So it's both, actually. So the 1.9 EV and the question, if you couldn't hear, was are these numbers real or are they coming from calculations? So the ground to excited state transitions have just been measured spectroscopically. So that one is pretty well established. The exact position relative to the valence and conduction band edges is not that easy to get spectroscopically because if you just look for when it ionizes, then you also have to worry about whether or not there's some like Frank-Condon factor or something that you have to worry about, right? And then that would give you a delta on that ionization energy. So there are a bunch of like old-timey measurements where people did things like photoconductivity, where it's less susceptible to that. Basically, you can do it's sort of like an Auger spectroscopy kind of thing, where you go and just measure photocurrent as you ionize a whole bunch of other defects, and then you see when these guys also, and then you can see you can fit some like inelastic tail, and then all of that matches the DFT pretty well. Although I should be careful when I say that because I think there is. Are there DFT people in the room? I don't want to like cast too much shade on DFT. but okay, let me put this in the positive way. The positive way is that it is very challenging to do DFT of your molecule and this extended lattice at the same time, right? There's just kind of a size mismatch. So you have to choose where you're going to spend your resources. Are you going to do it in trying to get rid of all of your boundary condition problems? And also these things are charged, so that apparently gives rise to a lot of issues that you have to like have something that compensates the charge, and then the question is that interaction kind of screwing up your calculation? So things like where is this ground state exactly relative to the band edge are actually very important because that essentially gives you something like a charge transition energy, right? Like it tells you that if I can move the Fermi level above this, then I know that that level is occupied, but if I move the Fermi level below it, then it's unoccupied. So these are really important. And the DFT folks have a lot of tricks for being able to overcome the size mismatch problem. But my personal impression from now over a decade of working with such folks is that they agree extremely well when there already is spectroscopic data. So I'm not sure how good the actual just like ab initio predictive value is yet. And I don't know why, I have to say. And they're very non-committal about why. So for NVs, these are extremely solid. For new defects, I would say there's still sort of a lot of open questions about what exactly people are seeing and where all these energies are. But we're now like, what is it, 2025? We're now a solid 30 years into the project of NV spectroscopy. So I think this is pretty well known. Okay, so that's the electronic configuration. So now how do we actually optically access these states? So now what we need to know are the actual optical dynamics of the center. So if I just shine green light on this thing, then I can take an emission spectrum, and what we see is this very sharp zero phonon line that corresponds to that ground to orbital excited state splitting. And that's at 637 nanometers. But then we also see this extremely broad emission band. And if I had known that I was going to show this to you guys, I would have actually just put a spectrum in here rather than drawing it by hand. But it looks roughly like this. And that spans something like 100 to 150 nanometers. And then in general, the absorption spectrum is just going to be a mirror image of the emission spectrum to first order. So the absorption spectrum has this big peak at the zero phonon line, and then you have this kind of lumpy thing that comes from the phonon sideband as well. I think we can just skip that because it doesn't matter. But okay, so now what we want to ask is like, what are the dynamics if I shine green light on this? So one of the real appealing things about NV Center is not for quantum sensing per se, but just like vanilla normal sensing, like when people want to make things that operate as boxes that you can use for GPS-denied navigation, for example, is that all you need is a green laser pointer and a microwave source and like some photodiode. So what happens when I shine my green laser pointer on this thing? What I get is that if I'm in the m=0 spin sublevel, then I will excite the center, and it will relax down to the edge of this excited state manifold, and then just come back down. So I have a nice optical cycling transition where it just goes up and then comes back down and goes up and comes down. And of course, your optical transitions in general to first order are spin conserving, right? So I'm going to go into some particular set of this excited state manifold in terms of my spin orbit states, and that's what guarantees this kind of selection rule. However, if I'm in one of these other two spin sublevels, the ms= plus and minus 1 spin sublevels, then what will happen is I go into a different set of orbital excited states. And then these guys are much more susceptible to phonon coupling that gives rise to an intersystem crossing to the singlet manifold. Okay. Doesn't matter why. I can write down a very large number of reasons why. But for the purposes here, you can just kind of take this deus ex machina. Somebody just dropped a color center that has these properties. Okay. So we have a spin-dependent intersystem crossing, where if I start in one spin state, I get to keep on cycling photons forever. If I start in the other spin state, I end up over here. And over here, if you're collecting red photons, is dark. Okay. So this is, and then the key is that the reason that it's dark is the singlet state has a lifetime that is about 10 times or more the optical excited state lifetime. So your excited state lifetime is 12 nanoseconds. My singlet state lifetime is 150 nanoseconds. So that means if I just count photons in a window that's relevant to this 150 nanoseconds, if I was in one of the spin states, it would just look dark. If I was in the other spin state, it would look bright. Okay, so that's the basis of optical spin readout. And then it turns out, again, for reasons that don't matter too much, but we can just kind of take as fact, that when we go back down to the ground state out of the singlet manifold, that is also somewhat spin selective. So it tends to drive towards ms=0. And then what that means is that if I just turn the green light on and then just wait long enough, it will actually initialize my spin in ms=0. Right, so readout is not enough. You obviously have to have state preparation as well. Okay, so the way that a measurement sequence would look is that I have my, my green laser, my NV center. I shine green light for like a microsecond or something, so long enough that when I start, I'm in ms=0. And then what I can do is whatever microwave sequence that I want. So I just like wait and let it sense the environment. And then I turn on another pulse of light and use that to read out the spin state. So what does that actually look like? If I turn on my green light after my spin sequence, and then just count how many photons per second I get as a function of time, then if I'm in ms=0, it takes a while to build up excited state population, and then I just come down to some steady state. But if I'm in ms=1, because I have this intersystem crossing, I have a much darker center. But then eventually remember that it returns back to ms=0, so it should approach the same steady state. So given enough optical cycles, it will go back to the same steady state that ms=0 achieves. So that means that my readout is destructive, right? When I turn on the green light, I screw up the spin state because I reinitialize. But that gives me a nice window where, as long as I keep my counting window less than the timescale over which I destroy the state, my contrast between the two spin states is basically just the area between these curves. And then that gives me my readout fidelity. Okay, so, right. So the most simple experiment that you can do is spectroscopy. This is really screwing up my coffee drinking. Normally I get to write and then ask you a question, stare at the board together for a little while, and that gives me time to drink. But now I'm just going to have to explicitly take breaks. Okay, so what we can do is magnetic resonance spectroscopy with the photons. So I'm going to use this green detection to count the number of photons that I get, and then also concurrently apply microwaves that are going to drive the spin around in this ground state. Okay, so there's two different manifolds to keep track of. All right, so even just CW, if I do nothing fancy, but just apply all of these things at the same time, if I never applied the microwaves, I would just always be in 0, and then I'd keep on scattering photons, right? And then I would just have some steady kind of count rate. But then as I turn on the microwaves, what I'm going to do is drive some of the population into plus and minus 1, which then mixes up the spin state. And then my fluorescence is just proportional to the populations. So what I should see is a little dip in fluorescence when when my microwaves are on resonance with this magnetic resonance transition. Okay, so what I should see in general is I have some photoluminescence, I scan my microwaves, and then I get this dip. And then now if I turn on a magnetic field, these plus and minus 1 spin states should split because of the Zeeman interaction. And then what I should see is that this thing just breaks up into 2 different peaks. And now just by reading out the distance between these peaks, or just like the value of the splitting, I get a local measurement of the magnetic field. Easy enough? It's basically exactly the same as like vapor cell magnetometers, but way easier because you can use a green laser pointer. All right, so just taking a quick step back, like how hard would it be to find another NV center? What are the actual unique features here? Because as I keep on emphasizing in cold atoms land, all these things are very generic. You should always sort of be able to initialize and read out a spin under the right conditions. So the key unique features are that first, your qubit states are remarkably long-lived for the solid state. Our T1 is around 10 milliseconds at room temperature. The T2 is just determined by the magnetic environment. So if you just kind of synthesize a diamond and you aren't, and you just use whatever precursors you have lying around, then what you're stuck with is the natural abundance of nuclear spin-containing isotopes of carbon. So carbon is 98.9% carbon-12 and 1.1% carbon-13. The carbon-12 is net spin 0, so it doesn't matter at all. But the carbon-13 now gives you this little nuclear spin bath that can kind of flop up and down and give rise to magnetic variation at the position of the NV center. And then that gives you decoherence. Okay. So kind of the typical natural abundance T2s that people see are hundreds of microseconds, about a millisecond. If you isotopically purify, people can get all the way out to the T1 limit. Okay, the other kind of key is that the single centers are very bright photon emitters. Okay, so my excited state lifetime is 12 nanoseconds. In principle, if I could really collect every single photon, that should give me about 100 million counts per second. In practice, it's sitting inside a high index of refraction environment, which is very difficult from an optical aberrations perspective. So we actually get more like, this is out of date. Maybe we get like 1 million counts per second or something when we try hard. So we lose a bunch in our optical system, but that's like way more than enough, right? The dark counts in just off-the-shelf avalanche photodetectors is like a kilocount per second or even 100 counts per second. And that's all you're trying to do. You just need to get above your technical noise. I mention this because there's also a lot of work, including in my group, on things like rare earth ions. And those have a lot of nice properties, not the room temperature stuff, but you can do kind of, state preparation, optical readout, and a lot of things, but they are not very bright. So there's some selection criteria that's like these things actually have to be practical. Okay, and then the basis for room temperature ODMR, optically detected magnetic resonance, is really just this spin-dependent intersystem crossing and then the long-lived singlet. But it's a long-lived singlet that's like kind of in this nice happy zone where it's not too long. You could imagine that if the singlet state lived for many milliseconds, that would just really slow down my ability to do any of these experiments, because then now spin initialization would take milliseconds. And if I'm only collecting these photons every few milliseconds, what really matters for magnetic field sensing is just sensitivity, right? So what you want to do is write down on the x-axis time, like time on the actual clock on the wall, not fictitious experiment time, but actual human time, and then how small of a signal can I measure? And anything that goes into the overhead of your readout, like I needed to take a whole millisecond to initialize a spin, eats into that wall clock time. So the fact that I can run these experiments every microsecond is actually very important, because it means I can average down 1,000,000 times a second instead of 1,000 times a second. Okay, so sorry guys, what am I doing here? Okay, yeah. So let's talk about how you actually use this to measure dynamics. Usually you don't get to see that process where I look ahead, but now you have to see everything. Okay, so how are we actually going to use this to measure anything in the environment that isn't just like a static magnetic field that I apply in the lab? So the first thing is that I can do a really simple measurement that doesn't even require any microwave control, which is that I can just look at the lifetime, right? So I can prepare in an eigenstate and then just watch it relax over time. And what this is going to look like for NV centers is stupidly easy. I just turn on the green light, put it in spin 0, wait some time, and then turn the green light on again, and then do this little readout pulse. And what's going to happen is that any kind of non-unitary dynamics will drive this spin into a mixed state. So then I will just get lower fluorescence that should all go out to a population of a half as I wait. Okay, so now let's assume that you have some magnetic noise that comes from some nearby sample. Like to make this really concrete, let's imagine that I have a chunk of metal, and that thing has electrons that are moving around in it, right? It just has some resistivity. And then the noise that is going to give rise to is Johnson noise. Okay, so I should be able to detect some noise that is broadband, because Johnson noise just goes as temperature, so it's completely white. And that is going to have some component in the spectrum that is on resonance with the NV center, right? So at around 3 gigahertz. Okay, so what we care about is this B of t with some spectral content, so B of omega t. So what the NV center is going to see is some fluctuating magnetic field that couples to the spin. And then what Fermi's golden rule gives us is that 1 over T1 is just going to be proportional to the spectral density of the B field that is perpendicular to the quantization axis, right? What we care about is stuff that's going to tip the spin vector this way. Okay. And what we can do is now write this perpendicular component in terms of a 2-point correlator in the magnetic field in time. So it's just going to look like the integral over e to the I omega naught t with this 2-point correlator between b at some time, b plus and b minus at some time versus time 0. And then what we can do is generically kind of take this magnetic noise and use it to learn about the material, okay? So if I just have, my material has some AC response that I can write down as some conductivity as a function of Q and omega, then I can convert this into a current noise correlator by fluctuation dissipation, right? And then now that current noise just gives rise to a magnetic field because of BO sub r. And then that gives me some magnetic noise. And then now I can plug that into Fermi's golden rule and turn that into a relaxation time. Okay? All right. This only works if you are on resonance with this guy here, right? Because you're sort of picking out the spectral component that actually leads to spin lattice relaxation. So we can only sort of use this to study anything that's actually sitting at around 3 gigahertz. So if we want to study anything else, then what we can do is things like Ramsey spectroscopy. Okay? So what I'm now going to do instead is take my qubit, place it on the equator of the Bloch sphere, wait some time and let it accumulate phase, and then I'm just going to map the phase onto a population, right? So I do a pi/2 pulse wait, and then do another pi/2 pulse, and then do my projective measurement. And what this is going to give you is some, decoherence curve that is proportional to T2 star, and or that gives you a decay constant of T2 star. And then this, in general, sort of measures your quasi-static fields with as high a precision as your quantum sensor will allow you to. Right? So these are the best measurements. And then now, OK, so how do I do this really well? So you can also think of this problem as I start the clock with my population and then wait some time. And then if the field is a little bit different, then the population will evolve with a slightly different Rabi frequency, right? And then that's going to lead to a phase slip, a different magnetic resonance frequency. And that's going to lead to a phase slip between my two measurements, and that's what gives rise to this decoherence. So if I can run this clock for much, much longer, I get a much more sensitive measurement of this phase slip, right? At short times, we just haven't had enough time to accumulate phase, but at very long times, you get all the way to a pi phase slip. So what this means is that if I want to have an extremely sensitive sensor, this probably goes without saying, I just need the coherence time to be very long. Okay, so the game is make something that has a long enough coherence time that I can actually measure the tiny fields that I want to measure. If it's decaying, then the only thing that I'm measuring is its decay, rather than the environment. Okay, so this is for quasi-static fields. Now, if I want to extend this to higher frequency noise, what I can do is many forms of AC sensing. So the idea is that I can use dynamical decoupling to now move the spin around coherently. And then that's going to allow me to decide what fields I look at. Okay. So the most simple dynamical decoupling sequence is a Hahn echo sequence. So I'm going to do pi/2, let it accumulate phase, and then a pi pulse. Actually, it's easier to do. I always do like the wrong axis, and then I'm doing a crazy dance in front of everyone, but I can just do like this axis. Okay, so I let it accumulate phase, and then I just flip around that axis with a pi pulse. Yoshi is laughing because she's seen me make that mistake in person before. And then now, if it's really quasi-static noise or quasi-static fields, then the time evolution, as long as you have a balanced sequence where you have the same exact time delay in both halves, then whatever happened here is now just going to reverse, right? Because they just keep on going in the same direction. And then they should just rephase and then come back together. And then now I get all of my population back at the end. Okay. But anything that is not quasi-static is now just going to show up as a decoherence term. So what this allows me to do is get past my T2 star limit and extend the coherence time of my sensor out to some T2 for this dynamical decoupling. And that allows me to do much more sensitive measurements. Okay. And then generally, you can kind of do whatever you want between these two pi/2 pulses, right? So I can put in lots and lots of pi pulses. That's called CPMG, car per cell by Boom Gill. It was an interesting enough idea in the 50s that we had to name it after 4 people. And if you imagine, for example, that I have an AC magnetic field that is, this is like a terrible diagram because it's not actually synced up, but but is synced up with these pulses, such that every time the phase of every time you do a pi pulse and the NV center is accumulating the opposite phase, you also flip the AC magnetic field, then it's just going to keep on accumulating phase from that part of the signal. Okay, so it's going to cancel everything else out, But then now the stuff that is, you're sort of maximally sensitive to things that are exactly commensurate with the sequence that you apply, and now you have a giant phase accumulation. You're very sensitive. Okay, in general, you can kind of formulate this as a filter function problem. So for a given pulse sequence, you can write down a spectral filter function that tells you what components of the noise you're actually sensing. What is our timing on this? Somebody tell me. Is it 9:45 or 10?
It's 10.
It's 10. Oh, we have tons of time. You're probably going to get a longer break. Okay. So, yeah, do we really want to go over the filter function? Yeah, okay. I guess it's helpful to think about these things concretely in terms of these correlation functions again. Okay, so in general, for some dynamical decoupling sequence that has some particular filter function as a function of frequency and evolution time, and usually these things look like these kind of sines and cosines. So you end up with some crazy thing that is sharply peaked around omega equals pi over tau. Then what you're going to be doing when you do a T2 measurement is you're just measuring sort of this quantity where you're integrating over the filter function, and then the component of the spectral noise density of the magnetic field that's perpendicular to the quantization axis. Okay, so as you change the magnitude of the magnetic field, that changes your magnetic resonance, and that's what gives rise to this dephasing. Okay, and then this, of course, we can write down in terms of a 2-point correlator in the magnetic field in time. Okay, so that's T1, and that's T2, and that's how we're going to measure all of the dynamics. Are there any questions before I get into like a much weirder topic? Crystal clear. There's an actual quiz at the end. There's not a quiz. Okay, so I would say that all of the work that's been done in this space for 15 years, 20 years, 80% of the work done in the space is really just measuring static magnetic field. And then another 20% is either measuring T1 or T2 to try to get at some particular quantity. And some of it is condensed matter facing. There's also kind of a big push in the field to use this as a tool for nanoscale nuclear magnetic resonance. So you can kind of take your NV center, put it next to like a bath of some molecule or something like that, and then use it to actually look for the added noise that comes from the Larmor precession of nuclear spins in that molecule. But those are essentially, the kinds of measurements people are doing. Is they just ask, for my single NV center, what is the static field, or what is the noise, and then maybe you do some spectral decomposition. Okay, so another thing that we have access to, because these things are, pinpoint spatial sensors, is that you can imagine also looking at spatio-temporal correlators, so not just temporal correlators. Let me motivate this somewhat concretely. So let's imagine, let's go back to my example that we talked about when we were working out the mapping through Fermi's golden rule and Biot-Savart and everything, which is that I'm just staring at some metal. Okay, and this metal has current that kind of bounces around like this with some inelastic mean free path. Now, what I can ask is, and then as these things are bouncing around, of course, the current gives rise to a magnetic field because of Biot-Savart. So if I just ask each of these NV centers, what do you see? Then what are they each going to report if I just have this ballistic transport? Like I have a whole bunch of NV centers, and I get to ask each one, what do you see? I'm going to cold call the Princeton kids. Ciro just got really, really nervous. Okay, what you see is white noise, right? So all of them are just going to say, I see Johnson noise. It's very boring. We all see exactly the same thing. Okay. But now I can ask a different question, which is, you can imagine I have two NV centers that are really close together compared to this inelastic mean free path. And then now these two, on average, are always seeing the same exact electron transit both of them, right? So I can ask a different question, which is the noise you see correlated, or is it uncorrelated? And now if I have a way of measuring that correlation function, then if my two NV centers are really close together compared to this inelastic mean free path, they'll say like, yeah, it's super correlated. We always see the same thing all the time with the same phase and everything. But then if you measure two NV centers that are much farther apart than this inelastic mean free path, they'll say, we see totally uncorrelated noise. What the hell are you talking about, right? All right, so how do I get access to this correlation function just by measuring my qubit sensors? So I can do a very, very simple measurement, which is that I take both of my NV centers and I just do a Ramsey on them simultaneously. Okay, and then you imagine that each of them is going to have some correlated component of the noise that has some, part of the phase that they accumulate that comes from this correlated noise. And then maybe they also have some local noise that comes from local nuclear spins or something like that that's at much shorter length scales. And then at the end of my Ramsey, remember all that I do is map this phase to a population and then read out that population optically. And when we say read it out optically, what we mean is that I detect some number of photons and then I write down that number of photons. So what my measurement actually looks like is a big array, right? And then I repeat this over and over again, okay? And my measurement just looks like a giant array where I repeated this measurement 1,000,000 times and then I wrote down a list of 1,000,000 numbers that were just the total number of photons after each measurement. Okay, so now I can just take those, and I'm going to call those S1 and S2. So I just have two classical arrays of numbers, right, that I've just written down. So now what I can do is define, for example, a Pearson correlation, which just says if I look at S1 and S2 and then look at their covariance and then normalize by their individual variances, then that's going to tell me sort of how correlated these two different traces are. This makes a lot more sense if I'm actually writing it out, but let's just talk through it. So let's assume that we have sort of, perfect readout, so we don't have to worry about, what added noise we have from our readout. Then if I have some spin correlations that look like, some correlator between MS1 and MS2, then that's just going to look like this as a function of the phases. So you just get a bunch of correlators between your sines and cosines. And then you have to make a few assumptions to make this nice, like the mean is the same as the variance, which is fine as long as you're in the presence of Gaussian noise. And then now what I'm going to do is write down this Pearson correlator as a function of all of these phases. And then this is going to be, okay, so then you get these sines and cosines, and then I can just rearrange them, and what I get is that just looks like some e to the I phi, and that's just my decoherence, right? So I just have some total decoherence of a single NV center that looks like e to the minus chi of t. And then now what I can do is write down my, my Pearson correlator in terms of this decoherence function, and then this correlation in the phases of the two different NV centers. Okay? So in some sense, you can think of this as this gives me my local noise, this gives me my correlated noise, and then this is how I'm able to separate the two of them out. Okay. So if we assume that the phases are the same, then this Pearson correlator just looks like this, where we have some e to the minus chi 1 plus chi 2. So I pay sort of a penalty of a factor of 2 if these if these decoherence rates are the same, if the single NV decoherence rates are the same. And this is very generic to quantum sensing, right? If I add a sensor, it's worse. It's better because I get better statistics, but if everything was perfect, it's worse because it decoheres faster. Okay, so we also pay that penalty here. But we also measure this correlated phase twice as fast. So it's kind of okay. Okay, so that's the perfect case. Are there questions before I move on? Most people go into this topic totally cold. Have spent zero time thinking about correlators. I know that I did. Yeah.
Here's some coefficient if I'm not wrong, captures linear correlation. Is that sufficient in this case?
You mean like should we be looking for higher order moments? Yeah, I mean, so the question of whether or not there's anything interesting to capture in higher order moments is very interesting and is definitely worth looking into. But for if you only have two sensors, it's actually hard to do anything higher order. You sort of need to go up to n sensors in general. It's not exactly right, but in general, you need to. Yeah, and that's what separately we've also been thinking about, like 3-point correlators and 4-point correlators. I'm told by my condensed matter theory friends that there's no point in going beyond 3 or 4 because their brains stop working. So you don't need to think about it at all. Yeah.
Does it help if these sensors are entangled to begin with, or it differs?
Excellent question. I will actually show you data. But there's no need to be mysterious. So the short answer is, so I haven't gone through the readout noise thing. We will talk about readout noise. But in general, yes. So with entangled sensors, you gain the standard factor of √2 that you would always get if you prepare your two NV centers in a maximally entangled state. But in the case of noisy sensors, where you're nowhere close to the quantum projection limit, then you actually gain by however far you are from the quantum projection limit. So because NV centers are very noisy sensors, we actually win when we do our entangled sensing stuff by √2 times 40, roughly. So there's a huge gain. Yeah?
How hard is it to actually entangle NV sensors? Like we went back to like our criteria for a good sensor and added in the criteria that we could like entangle a large system of them. Would NV sensors still be like the best sensor?
Well, large is super hard. That's too hard. 2 is not so bad. I would say that making just 2-particle, maybe 3-particle Bell states is, well, let's talk about it in the second hour. But I would say 15 years ago was a total hero experiment. Now we've figured out some tricks where it's not so hard. If you wanted to make a very large entangled state, I think this is probably, well, I shouldn't be so glib. There are some very interesting and creative ideas, particularly from Norm Yao and Anna Maria Ray, about if you have kind of a messy dipolar strongly dipolar interacting system. So not everything that I do, I can write down what I'm going to do before we do it. It's not this very messy stuff. But if you just imagine I have a mess, a very strongly interacting ensemble, one question is, can I drive it into some sort of entangled state, right? Like a squeezing kind of thing. And honestly, the squeezing doesn't work that well. But there's probably other ideas that are a little bit like that and aren't exactly squeezing that are kind of interesting.
Say if you wanted n sensors, in some error corrected code space, I guess the jury's still out, how we do that experimentally.
Yes, correct. Jury still out is a very nice way to put it. I would say it's well, okay, no, sorry. Again, I should be nicer and more careful and more positive. So you could imagine one resource that you have is that you don't necessarily just need to use electron spins as your sensors, and you also don't need to use them as your only quantum resource. So the NV center kind of rides with a whole bunch of nuclear spins that are nearby, And like on average, you always have one strongly coupled nuclear spin. It's like in 99% of the NV centers within your coherence time. And then if you have some way of extending your coherence, then you could easily make a register of like 2 or 3 of them. And then of course it has its own native nuclear spin, like the nitrogen always has a nuclear spin. So that forms kind of a nice little register. And then you could imagine doing a lot of quantum error correction locally on like 1 or 2 NV centers. So if instead of thinking of it as I need to make an n particle entangled state, but instead I have, what I have access to is like n pairs that I can make Bell states out of, and then each of those pairs has a little quantum register attached to it where I can do local error correction. It's a slightly different regime than people usually think about, but that's the resource that we have. Okay, readout noise. All right, so in reality, you actually have an enormous amount of readout noise. And we normally don't talk about it at NV land because it doesn't sound so great. But when we rely on this inter-system crossing to do our state readout, right, you just have the shelving state that lasts for a few hundred nanoseconds. And I already told you that we only get 100 kilocounts per second, optimistically 1 million counts per second. So in general, you only get something like 0.03 photons per shot. So most of the time, when you imagine this little array that I said, we just write down the number of photons, that array is almost all zeros, right? So most of the time, we're waiting in the dark, and then you get a little blip. Okay, so we can capture this in terms of a readout noise parameter. So if you imagine that I have some number of photons that I get from one of my spin states, so from ms equals 0, alpha 0, and then another like average number of photons that I get from the other spin state, alpha 1, then my readout noise in general is going to look like this, 2 times alpha 0 plus alpha 1 over alpha 0 minus alpha 1 squared. So you can see that as I can separate these distributions more, my readout noise goes down. Right? So the picture you should have in your head is I make some histogram of how many counts I get in one bin, and I just want like very cleanly separated distributions to get good state readout. Just the same as all qubit readout tasks. Okay, so this is bad that you have this huge readout noise penalty. Because now you're going to have some total Pearson correlation that you can measure that looks like the ideal correlator or correlation divided by the product of the readout noise of both of your NV centers. And for NV centers, generically, we're at around 30 to 40 times the quantum projection noise limit. Okay, so this is 1 over 40 squared is your prefactor. So this is very, very hard to measure. And then, so because this goes as readout noise squared, that's really bad. If you actually calculate the time that it takes to measure a signal, that actually looks like readout noise to the 4th power because you have another squared from your signal averaging. So this is like catastrophic. And that back of the envelope calculation, it wasn't exactly this formal, but that back of the envelope calculation is why several theorists who will remain nameless told me that this experiment was impossible. So the answer in the end is that as long as you can come up with clever ways to reduce this readout noise, then this correlation becomes sort of possible to measure. And then we can talk about like all of the other technical problems that ride along with that later. Okay, but so your general strategy here, is this my last slide? Oh, this is my last slide, okay. Your general strategy here is that what we're going to do is just take a bunch of NV centers and then measure this Pearson correlation as a function of space. And then I'm going to use that to get a 2-point correlator in the magnetic field. And then I can also do things like spectroscopy. So I can do this 2-point correlator in the magnetic field using all the T1, T2 stuff that we talked about earlier. Well, let's say the T2 stuff. The T1 is a little less clear what you're measuring there. And then use that to get, for example, B of omega x1, B of omega x2. And then there's yet another kind of part of parameter space where as long as I can independently control my qubits and start the clock on them at different times, then I can also add a time parameter to this, right? So in general, I can measure B of omega x1 t1, B of omega x2 t2. And then I'm told by the condensed matter theorists that there's no reason to think about this at all. But the last thing that you can do is also just drive with totally different pulse sequences. So you can imagine doing like, XY8 on one of your NV centers with some pulse spacing and XY8 on the other NV center with a totally different pulse spacing. And then now what I have is B of omega 1, x1 t1, B of omega 2, x2 t2. But supposedly frequency-frequency correlators just like don't make any sense in condensed matter. So we'll see if that ever has any use. All right, any questions? So I'll just soak up like 1 or 2 minutes with a small rant, which is that normally, I think if you go to a quantum sensing workshop, tutorial, whatever, there's sort of like a funny, I wouldn't call it a fight, but broad disagreement in the field about what the term quantum sensing means. And I personally find such fights just very tedious and stupid. So, so let me just dispense with it here. So I think, okay, and there's a lot of young people in the room, so I'll explain to you how the sausage is made here. The reason that there are such fights is because there are buckets of money, and then the buckets of money are labeled, this is for quantum sensing. So then everyone tries to like figure out, what does that term mean so that I can try to get my part of this bucket of money. Okay, so I would say that there's sort of one flavor of quantum sensing, which we have been doing since the 50s, right? Which is that you take a controllable quantum object, and then you use everything that we know about unitary dynamics and non-unitary dynamics, and then use that to sense the world around you. So in that sense, vapor cell magnetometers totally count. All of this atomic fountain stuff count, like it's all fine. we can be nice. And then there's another sense of quantum sensing, which is, I guess, like some people like calling quantum 2.0, where you take some of the weirder aspects of measurement and entanglement to try to get an advantage, right? And you say, like, with entanglement, I'm going to make a better sensor than I would have without entanglement. And if you go to these meetings, I apologize to everybody if you ever go into this field and then you are subjected to this annoying fight. It is stupid. Maybe the new generation can just stop it forever and ever. But then people will just like yell at each other about like, do you really have quantum advantage, right? Like did you really prove it? And it's just such a stupid fight. But here's what I will say about it. Here's why I think it's really dumb. One, it's clear that kind of demonstrating these principles is really interesting, right? That like we sort of exercise how well do we understand quantum mechanics? How well do we know how to harness these resources? But the second is that what they're fundamentally fighting for at the end of the day is like a factor of √2, and that just doesn't matter. That is different. It is fundamentally different from the quantum advantage in quantum simulation or quantum advantage in quantum computing fight, where the possible prize at the end is exponential. Okay, so if what you're fighting over is a factor of √2, it just never mattered to begin with. So here's the reason why. So here's what I think is interesting. Okay, what I think is interesting is that there are some cases where the factor of √2 matters, but those are all like actual technology cases. So it's not just I have my Nature paper, but it's really like you did a thing and then you did it way better because you added this factor of √2. And the paradigmatic example of that is LIGO. Okay, LIGO, but what did LIGO take? So what LIGO did was they engineered the crap out of this interferometer. They did every single thing that you could do to beat down every source of technical noise. They turned up this laser all the way up to the point where they were back action limited. And then, only after a couple decades of work and hundreds of people, did they then turn on their little squeezed light source. And then they got their factor of 2. But the amazing thing about the factor of 2 is that what that means is they can see 8 times more universe. So in that case, it really mattered, right? The place where it mattered is it allows us to see things that we literally could not have seen otherwise. So my plea is, let's stop fighting over factors of 2, and instead think about things from the perspective of, can I measure something that is fundamentally different from what we were able to measure before because I've added this quantum sensor? So from that perspective, sort of what's motivating a lot of this, can we see correlation functions? Can we look at dynamics? Is that when I look across the field and see what kind of probes people have, they do not have ways to see dynamics, and they do not have ways to measure these correlation functions in real space in real time, right? And I think like that, this is a place where you could plausibly have a completely new thing that you just can't measure otherwise. And then that sort of goes back to this question about, like, can you just make these large entangled states? Is this a good system for doing that? I think I would like to turn the question on its head and say, instead of saying, let's make a large entangled state to just measure static magnetic field with Heisenberg scaling so that we can do a factor of √2 better than this other scheme, let's instead ask, if I make an entangled state that's like a little entangled or something, or has this particular entanglement spectrum or something, then does that give me access to fundamentally new quantities that I wouldn't be able to measure otherwise? Okay, that's my rant. Everyone can go have their coffee, and then we'll come back and just do a research talk. All right, thanks, guys.